I'm going to give you today just an introduction to some of the sorts of thinking you might have to do. This won't be perhaps a typical lecture, but it'll incorporate elements of many of the classes we're going to have. In particular, we're going to be using these voting packs that you've all been given, so that what we're going to do is, every now and then I'm going to ask you a question, I'm going to get you to vote on the answer, and that will give me some idea of how much you've understood or how well you've done so far. But on the other hand, the first vote might be somewhat of a guess. After that, I'll give you a chance, quite often, depending on how the vote goes, to try to persuade your neighbour that your answer is right. Now, this is good for everyone because the people who do know the right answer will have the experience of trying to explain it to the other people who don't believe them. And the people who don't know the answer will have the opportunity to get the correct answer. Of course, it may well be that people with the wrong answer are more convincing than the people with the right answer, in which case it may be that things get worse on the second vote, but we'll find that out as we go. Okay, so what's the purpose of these recordings that I'm going to make of these lectures, assuming the IT equipment works out properly? Well, I would say what I most like, when I ask for feedback on what people use the recordings for, the ones I really like are the people who say, there was a bit in the lecture where I wrote down the lecture notes, and I got to this bit and I was thinking about it, I still didn't quite understand it, so I just fast-forwarded to that bit of the recording and had a quick listen to what you said at the time, and that gave me that little bit of extra information that really helped. So I think that's one of the really good uses of the recordings. You can go back and see what I actually said, because I won't write down everything I say. For example, I'm not writing down what I'm saying at the moment. Okay, so we're going to launch straight in to an old riddle. This is a famous old riddle, so I certainly didn't invent this. Goodness knows how long it's been around for. And it's in slightly archaic language. So a man looks at a photograph and says, "Brothers and sisters have I none, but that man's father is my father's son," pointing at the photograph. Brothers and sisters have I none, in case you're wondering, means he's got no brothers and sisters. No siblings. So you haven't had enough time to think about this. So maybe you've all seen it before, or maybe you've all worked it out. This doesn't look like maths, but I have to say that I think it's mathematical, or at least logical thinking in disguise, and I regard it as a two-stage problem, a problem that's easier if you break it down into easier pieces. And that's often what you have to do in maths, break things down into easier pieces. So what I'm going to ask you to do is go for an initial vote. I'm going to let you have another 10 seconds to think about it while you get your voting paper ready, and then I'm going to see whether everybody already knows the answer to this one. Now, I prefer you to keep the voting papers in the pack, as it were, because it's got a white background, and then the people behind you don't know what you voted. I want to discourage people looking around to see what everybody else has voted, because we really want to see what people are thinking at the moment. Okay, now let's get everybody to vote. I want to see what people have gone for. And what we've got is most people going for number 3, his son, with a significant minority going for the person himself, on number 1, and a few other votes, but mostly going red or green. But there's quite a few reds around there. So, okay, the majority have gone for green, and some of you have gone for red. Let me make it a brief discussion then, while you just talk to whoever's near you and either confirm with each other that you're really sure about your answer, or try to persuade the person near you that your answer is the right one and their answer is the wrong one if they disagree. Okay? But I won't give you the full 5 minutes that I normally would. I'll just give you 2 minutes on this one, and then we'll re-vote and see if the answers have changed. Okay? So have 2 minutes to think about it. I'm going to pause the recording. Okay, so you've had a couple of minutes to think about it. And let's see what happens on the re-vote. Let's see what everybody thinks on this version. And we've got almost 100% going for green now. We have a few people holding up for red. And I will now reveal that green is the right answer. And you've now, no, sorry, that's some TV program. So let's think. I'll just give you some idea of how I would break this down, because you've probably done the same thing. I've looked at that is my father's son bit and identified what that means. And because I've got no brothers and sisters, well, okay, this is not actually true, but that person has no brothers and sisters, and so their father's son has to be themselves. So that's himself. But you haven't finished by the time you've done that. As I said, it's a two-stage problem, and you break it down to easier bits. So now you substitute in, and you get that man's father is me, because the my father's son bit is himself, so he'd be saying me. And if that man's father is me, so that man is my son. But if you ask people to make their first guess on this one without giving them any time to think, a substantial proportion of people will say myself. And the reason for that is that they hear the whole sentence, and it's a slightly complicated sentence, and then they start processing it, and they work out that my father's son is me, and at that point they forget about the rest of it, and it comes out as and they answer myself, because they think they've solved the problem. And of course you have done the hard bit of the problem, but there's still a second stage just to finish it off, the substitution in. And that's essentially maths and a bit of logical thinking, in disguise. Okay, so let's move on from that. As you go through your course here, you will find that some of your modules give you lots of techniques you can use to get answers to problems. I hope there are a few spare handouts still at the front. So you'll learn techniques how to do problems. You'll learn some recipes how to solve standard problems. But sometimes you're going to need to have ideas. Sometimes you're going to need to know how to solve problems. You're going to need to know, this is what our teaching officer always says, you're going to need to know what do you do when you don't know what to do. And so you're going to have to learn how to mess around with problems, think about them, try and get some ideas in order to solve them. But still, as you go through, some of your modules that you attend will be about pure mathematics. And in those modules, you're going to see a whole load of definitions and notation and questions and statements, really careful, rigorous statements that seem to have all the T's crossed and I's dotted, and a lot of care has been taken over how they're expressed. And then they're going to be proved, and a proof is a bit of a strange thing. If you haven't seen many proofs before, these proofs that all start in this formal language, like let n be a positive integer, and then suppose that m is another positive integer, and so on, stuff like that. And it all seems a bit of a fuss, especially if you think that, well, you can be pretty sure that something's true before you start, so why are we having to prove it? So here are some of the questions you might ask about proofs and definitions and things like that. On the whole, mathematical statements you've met, maybe you don't know immediately what the answer is, but you try a few examples, you spot a pattern, and you figured out what the answer is. So why do you have to go away once you've figured out what the answer must be, why do you have to go and check it properly to be absolutely sure? Isn't it always obvious? So yeah, why should we prove anything? On the other hand, you may have another point of view, which is, well, no matter what you do, you can never be quite sure. You can check a million cases, but how do you know that it's true for 1,000,001? Can you ever really be absolutely sure that it's always true? This one here, you'll see proofs of things that you think are blatantly obvious, and yet they'll get given a really careful mathematical proof. And you may wonder why on earth that's going on. And there are these really careful definitions. You know what a rectangle is. Why would anybody want to write down a definition of a rectangle? Or a square, or something like that? Why would anybody want to write down a careful definition of one of these things? You know about prime numbers. Why would anybody have to write down a really careful definition of what a prime number is? Because you've been working with prime numbers already. You already know what they are. And the final question that I get asked later in my modules, when I've done lots of proofs on the board, and people have seen lots of proofs, people ask me, well, do we have to memorize lots of proofs? And to which the answer is, I hope not. I'll just say you will be expected to do some proofs in the exam. Proofs are bound to turn up in the exam. Some of those proofs might be exactly the same as some proofs that I've done in classes. But a lot of the proofs that come up will be variations on it. Simple variations, I hope, but I'm not so interested in you memorizing proofs, though it may be a good idea for you to spot any interesting tricks. What I really want you to do is to develop an ability to write proofs for yourself, construct relatively simple proofs, and as we go, I'm going to do my best to give you examples. So I'll do proofs in class, and if you understand those proofs, that may help. But the only thing that really helps you to do proofs is to try to do proofs yourself. And so I'm going to give you lots of chances to practice doing proofs yourself, and I'll try and have quite a variety of them. For example, in the exam, there's a section A and a section B, and a section A's got short questions, and section B's got longer questions. They've got equal weight, but the section A you've got to do 5 short questions, and they're all compulsory. Section B has got 3 longer questions, but you only have to do 2. In the longer questions, you might have to prove something that takes a bit longer to prove. In the shorter questions, anything you're asked to prove is likely to be quite short. You won't only have to do proofs. You may be asked to state some standard results that's got a name, state some named result or other, or state some standard fact. Things like that can turn up. So there are various standard things can turn up, and then there are other bits that won't be standard at all, and there'll be everything in between. There'll be stuff that looks like things you've done in classes, and things you've done in the question sheets. And there'll be other stuff that looks really rather different. And there'll be a whole variety of stuff coming up on the exam. So the best way to approach it is to try and really understand the stuff, not to say, this is what I need to do to get a pass, or 60% or 70%. This is what I need to do, and I can ignore this lot. The more you understand, the better your chances. And there is no easy route to doing pure mathematics. If you take shortcuts, that means you're getting reduced understanding, and that gives you a reduced strength background. But I haven't answered these questions. I'm hoping that you'll get answers throughout the module to the questions I've raised here. And we're going to look at a few things today which might help to partially answer some of them. So let's see what we've got next. Now, this question is actually slightly harder than most of the questions you'll meet in the module, I would say. As a result, it's going to give you a chance to do a bit of thinking, and you may need a slightly longer discussion, and then we'll see whether anybody's got any ideas. But what I'm going to do is I'm going to give you a short time, and then I'm going to get you to vote, and then I'm going to give you a longer time to talk to each other about it. So I think for the first one, try to have a think of it for yourself and see if you can come up with an opinion. You may well have to guess. That's absolutely fine at this stage. See if you can make a guess. Then you can have a longer time and see if anybody's got any ideas as to how it might work. Then we'll have another vote. After that, I will probably help out, but maybe somebody will have had some ideas by then. Not a particularly easy one, this, okay? But it will illustrate that proof can help you, not only does proof help you to know things are definitely true, it can also really show you why something is true and help you rethink about how the original problem was posed. Okay, so I'm going to give you half a minute to a minute to think about it for yourself, and then I'll get a vote. It's fine to guess. It's not an easy problem, and then we'll see what you think. Okay? So I shall stop the recording now and give you a minute to think about it, and then we'll have a vote. Okay, so if we can have an initial opinion as to what the people think. Okay, so looking around the room, I actually see every possible answer, but with a majority going for green. They're going for just one, but with a significant minority going for infinitely many, and a few going for some of the others, okay? Right, so what I'm going to do now, again, is there are two different things you do in this discussion. One is try and persuade your neighbour you're right, but the other is, can you prove your answer, or is it just a guess? So, can you actually prove it? Now, when I get the next vote, after I've given you a chance to think about it, I promise I won't pick on anybody to ask them to explain their reasoning. I'll make that an optional extra, which I'll ask for at the end, okay? So I won't pick on anybody without warning when you do the next vote. I want people to feel safe when they vote. So nobody gets picked on the next answer. But I will then, after that, ask whether anybody's got any ideas as to why their answer might be true. Okay, so we'll now pause the recording again. And I'll give you 5 minutes to persuade your neighbour or get together and try to think up a really rigorous proof as to why it's true. Okay? Okay, so the next thing to do is to go for a re-vote after you've had a good chance to discuss it. And let's see whether people's opinions have changed. Okay, so we've got a big majority of people going for 1, and a smaller minority now, rather small minority, going for infinitely many. Now, I will reveal that 1 is the correct answer. However, this isn't just about getting the right answer, because that could still be a guess unless you found a proof, right? So you can try a few prime numbers. You've found one that works. I expect that everybody's found one that works. And then you've tried some more prime numbers, and you couldn't find any more that worked. And then you might suspect that the answer is 1 because you haven't found any more. And then you want to back that up with some reasoning that justifies it. So now, my next question is whether someone is brave enough to put a hand up and suggest some reasoning. Yes? What have you come up with?
So I thought, seeing as it's 1 more than a perfect square, I said x squared equals b plus 1.
Okay, so 1 less than a perfect square, right? So x squared equals p plus 1. Okay, so we write x squared equals p plus 1. And your x is what sort of number?
Just a number. So it's not a square, so.
I know, but just to clarify, what sort of integer, yeah. So we're not going to write down the most formally worded proof necessarily with all the language. We will eventually have to do that, but for now, let's get the idea, okay?
So I thought 1 plus x squared minus 1 equals b.
Yeah. Good.
Factorize to x plus 1 times x minus 1 equals 2.
That's very good.
Okay, so assuming the statement is true, then p is a prime. So the two factors must be p and 1.
Okay, now there is a slight exception to that, but let's you would expect the factors to be p and 1, so, well, there's just a possibility that something could be negative, but we'll ignore that. Okay, ignore the negative ones for the moment. So there should be p and 1, okay? Yeah, minus p and minus 1 a possibility. Yeah, I know. Yeah.
So assuming x plus 1 is still 1. You know what I mean?
Yeah,
So if x plus 1 is still 1,
yeah. If x plus 1 is 1, then x equals 0.
0 squared is not a perfect square, is it?
Actually, it is a perfect square. 0 is a perfect square of 0, so I'd accept that. But even so, you'd have p plus 1 would now be x squared. So you get p equals minus 1. And that doesn't count as a prime number, okay? I'll put this little symbol here to mean that doesn't work, contradiction, right? So x can't be naught. Sorry. So it can't be naught. So then,
assuming that that's not 1, so that x minus 1 shall be 1.
yeah. So if x minus 1 equals 1, x equals 2.
So x 2 squared is 4, equals 2 plus 1, so it is 3.
Yeah. So p has to be 3. That's very good. So just have a little look at that reasoning again. You rethought about the original question. So saying p plus 1 of the perfect square is saying that there's some perfect square which, when you subtract 1, is prime. But perfect squares minus 1 factorize, which you don't normally do with prime numbers, because here it is a product of two numbers. Doesn't look very prime. But that's okay as long as one of the factors is 1 and the other one is p, or one of them is minus 1 and the other one is minus p, which is very unlikely in this case. Assuming, you might as well stick to positive numbers, x, because you only get the same ones again if you do the negative ones, okay? So we haven't done it in full detail. We've only gone for the reasoning here. And if you're writing a formal proof out, you would have to put a lot more English in. But the main idea is we factorized x squared minus 1. We factorise x squared minus 1. Prime numbers don't usually factorise. So we reduce the problem to checking a few special cases. And that's what you then did. And yes, you have to be a little bit careful thinking about the possibility that x could be negative, but that just gives you the same key again. So you might as well assume that x is positive as well, and positive integer, or 0, of course. You've got 0 as this possibility. You have to convince yourself that minus 1 isn't a prime number, and so on. But we won't go through that in any more detail now. You're going to see lots of formal, rigorous, carefully written out proofs later with all the language we need, and I'll explain why the language is important later as well. But so the answer is p equals 3 is the only possibility. Right. So I just want to point out that some of these questions are not quite so easy. You may remember that 3 squared plus 4 squared equals 5 squared, etc., so-called Pythagorean triples. And Fermat, famously, about 350, 360 years ago, whenever it was, wrote in the margin of this book that he'd worked out that this can't be done for any power bigger than 2, but that the proof is just too big to fit in the margin. And for 350 years, people tried to find out whether he was right. Obviously, we don't count things like 0 squared plus 0 cubed plus 0 cubed equals 0 cubed. We're talking about positive integers being raised to some power bigger than 2, like 3. So what happened was, people checked if value was right for 3, and they found it was right for 4, and they found it was right for 5, and they had lots of reasoning, and they showed it was right up for 40,000, powers 40,000, but none of that helped, because you needed something that worked for all powers. And eventually, Andrew Wiles came along, and with a little bit of help, was able to prove that it really worked. But his proof certainly wouldn't have fitted in the margin Fermat was trying to write in, because if you look at all the mathematics that Andrew Wiles' proof of Fermat's last theorem uses, we're looking at hundreds of pages of maths. So it's not surprising it didn't fit in the margin, nor could Fermat possibly have worked that proof out, because it used so much modern mathematics that nobody knew at the time. Did Fermat really have a short, elegant proof that didn't quite fit the margin? Well, that's up to you to decide. Nobody knows. There are a lot of false proofs out there. In fact, people are still sending in false proofs, I think, to mathematicians all the time, saying, I found Fermat's proof. But no short and elegant proof that Fermat would have been talking about has been found yet. Maybe you'll do it. Okay. Now, let's talk about fractions. We've got 2 hospitals, and they're competing over which is better at curing a particular disease. And they make the following claims. Hospital A claims that it cured a greater percentage of its male patients than Hospital B did last year, and that it cured a better percentage of its female patients than Hospital B did last year. There's no tricks involved here. We're talking about hospitals actually looking at their figures for patients who are either male or female, and they had at least one patient of each, and they either cured them or they didn't. No, there's no tricks here. I'm simply asking you a genuine mathematical question about fractions. Hospital B says, yes, they may have cured a better percentage of their male patients, and they may have cured a better percentage of their female patients, but we cured a better percentage of our patients than they did. And the first thing I want you to do, we're going to get a preliminary vote on whether you think this is possible or impossible. Now, I haven't said what colour is going to be what, so let's go for 1 red impossible and 2 yellow possible. And I want your honest, instinctive impression. So we're looking for red or yellow, red impossible, yellow possible. Okay, so if you could show for that. We've got quite a few of each. Is that a question at the back, sorry? No, okay. We've got quite a few of each. In fact, I'm not entirely sure which the majority is. I think the majority have gone for yellow, but if so, it's very, very close. and I'm not quite sure. Okay, so this is a really good chance for you to have a think about this. And let's have a few minutes. See, if you think it's impossible, try and come up with an argument that really demonstrates it's impossible. If you think it's possible, try to find some numbers that work. So try to come up with a little table of figures, if you can, to see if it works. Obviously, if it's impossible, you won't be able to find a figure. But that gives you two different figures you can try, just for a couple of minutes. We'll see if anybody comes up with something, at the end of which I'll tell you what I've got. We won't get to the questions about definitions at the end, so I'll have to let you discuss those with your friends. I think we're going to be finishing with this hospital one, and the questions at the at the end of this section are for you to discuss with your friends to think about whether you can agree about the answers to those. Okay, so let's have a go at this one. I'll give you a couple of minutes to think about it, and then we'll see what people come up with. Okay? So let's start with a re-vote and see whether anybody's changed their mind or whether you're still feeling about the same about it. What do people think? Is it impossible or is it possible? Well, I have to admit that it's still about even. So I think that the results so far are inconclusive, so nobody knows for sure yet. I'll reveal that the answer is that it is possible. Okay? Fractions don't always behave the way you expect, and this is in fact known as Simpson's paradox, that it is possible. And I'm just wondering whether anybody has come up with a nice table. I've got one, but let's see if anybody else has come up with a table. Yes, have you got a table of numbers that work? Yeah? Oh, okay. Let's so hang on a sec while I'll draw up a little table, and we'll draw the figures in there, and then we'll see if they work. So we've got hospital A, hospital B, males and females, and we'll put in the number of patients, or the number cured over the number of patients, or something like that. Okay. So hospital A. Well, yes? 70% male patients. You're going to need to tell me how many male patients there are, though, otherwise it won't be conclusive. Do you want to tell me how many males? It does actually make a difference. No, so the 70 out of 100 you're going to have, right? So this is our first try. We're going to try 70 out of 100 cured. So there are 100 male patients, 70 cured, okay? And can you tell me any more? Male patients, 30 female patients. Oh, right, sorry. Let me correct that. Okay, so I'm going to write it. I'll put the 70 on the bottom to indicate 70 males, 30 females, okay?
He has some female, 30 male.
Okay, good idea. Don't worry. That's not a worry. Do you have some that you think do work, or shall I try another one? Or sorry? Okay, don't worry about it. Okay. It's all right. I mean, don't worry. Things can go wrong. Things can always go wrong on the spur of the moment. But the point is that you've tried some figures and you've got the idea that it's probably right. And even if the figures that you first thought of don't work, you can try some more that do. I'll tell you what. I'll give you some that I thought of that I think work, and I may have got it wrong because I just scribbled these down a moment ago. So I may well make a mistake as well. But let's see whether my ones work. I've got 2 male patients 1 cured for hospital A, and 148 female patients, 2 cured for hospital A. I don't think you've done very well on the female patients. Hospital B got 52 male patients, cured 24 of them, which is less than half. And they had 148 female patients as well, but they only cured 1 of them. So they did terribly on the female patients. I'm not sure that as a female I'd want to go to that hospital. But if you look at the totals, Hospital A has got 3 out of 150, which is the 50th. Okay, so it's genuinely 150 patients, and they've cured 3 of them. 1/50th doesn't tell you how many patients there were, but that's just the actual percentage, 2%, right? Hospital B has cured 25 out of 200 patients, which is an 8, which is 12.5%, which is a lot better than 2%. So, because of the imbalance in the male and female patients, and because of the way these things have been distorted, and the fact that both hospitals seem to be pretty poor at curing their female patients, and anyway, Hospital A's had so few people cured that it could just be in the noise, fractions don't behave quite the same way you expect. So I would argue that this is this little paradox here, Simpson's paradox, as it's called, and look it up on Wikipedia or on the internet. Actually, it's a really nice example involving batting averages on the internet. There's an example that really happened where one guy had a better batting average on each of 2 test series than his brother, but his brother had a better overall batting average. So they had an argument over who'd done better. And you'll find that on the internet. It's a nice YouTube video about that. So my intuition, even now my intuition says this is unfair and that you should be able to check if you're better at each bit, and that should tell you you're better at the whole. But when the numbers come in balance like this, it turns out not to be true. And for me, that's an argument in favour of proof. Just because you think something is intuitively obvious, it might actually be false. And you're going to need to justify your reasoning if you want to be sure. I'll just show you the last slide. We won't have time to do it. These questions, problems 5, 6, and 7, you can't do them unless you know the definitions of the concepts you're working with. This is why definitions are so important. Change your definition and the answers change. Okay, that's all right. There's a standard test every Thursday morning about this time, so as long as it doesn't go on for more than a minute, we're allowed to stay. But we are finishing anyway, so there you go. So that's okay. So I'll tell you, discuss this with your friends about what you think the answers are. I won't give you the answers. In fact, the answers have changed historically. It turns out that the definitions people have used for these concepts have changed through history. As a result, the answers have changed as well, especially to problems 5 and 6. Problem 7 is an interesting one. I don't think the answers have changed that historically, but you have to make sure you know what a prime number is, and you have to check your definition against these. If you think you know what a prime number is, check your definition against this, and we better stop there because you need to get on to wherever you need to go next. Okay, so we'll stop there.